Good morning, sir. My name is P. Lakshman of Electrical and Electron Branch. Today, my topic is about method to improve the cathode ray oscilloscope accuracy. First of all, we have to know about definition of cathode ray oscilloscope. A cathode ray oscilloscope is an instrument based upon the cathode ray tube that provides a visible image of one or more rapidly varying electrical quantities. A cathode ray oscilloscope may be used to display the variations in voltage signals. And this is the schematic diagram and the picture which is we are using in the laboratory, and we are observing the waveforms and output and input voltages we are given. And description: distortion in the cathode ray oscilloscope limits the achieved accuracy in the split of piecewise linear correction and polynomial functions of the static and time-based nonlinearity corrections can be achieved 4 to 5 times improvement in accuracy compared to only the 2 times of improvement for linear corrections. And for fast transient waveform recording, this improvement is important in increasing the dynamic range and decreasing the waveform's noise also. And recording of the fast transient signals with sustained sub nanosecond raises time required. Cathode ray oscilloscopes CROs, these scopes have the about 4 effective bit accuracy which related to the distance from a measured signal to the recorded waveforms. The accuracy of CROs can be improved by the methods developed in this paper. The method creates the correction functions by fitting a surface to no discrete voltages and by fitting a smooth function to continuous deflection voltages. The both higher order polynomial correction functions which have the continuous derivations. And the first one is oscilloscope. The position pair value x and y refers to the geometric positions of the recorded waveforms on the CRO recording surface. With the approximate calibrations, those geometric positions can be converted to time and voltages with respect to T1 and I1, and the values are represented in the input form. The corrected A and Y will be noted by the R dash and Y dash. In this cross section, stretch of a cathode ray deflection structure, and the cathode ray is the solid line from the electron gun to the recorded surface, and the dot represents the x or dot y or and dot y represents the pair that chosen to read and sampled from the continuous beam tracked on the recording surface. The vertical deflection system is drawn as the plate A and the horizontal drawn plate B, and dashed line is the no deflection voltage beam position. The distance is from no deflection to the current position is R. We observe in the pictures, and we are gun and the CRO we are observing the waveforms. And the next one is the static distortions. If the static or fixed DC voltage are applied to S and Y deflectors of the scope, the beam position of the ideal CRO would be a linear function of the voltage, but in fact the deflection is not perfectly linear, and is distorted and impale the fit to maybe grid of known as horizontal and vertical voltages. The order of the polynomial surface is used can be chosen as a third order since the theory of electron beam aberration gives the distortion proportional to the R3. The reference of the static beam is a built-in function which the CRO records as a matrix of the DC assorting I dash and the y positions known as the voltage points plotted. The measured discrete data pointer as shown as the circles and the desired ideal positions of the beam as shown in the crosses. The large diversions of the measured data from the ideal positions should be about 1%. And the next one is the time-based non-linearity. CRO has the time-based generator which is not perfect and it is non-linear. Since time is derived by a voltage ramp and the linear voltage ramp yields the similar linear conversion from the R or position to be time to time, and the reference for the time-based nonlinear is the measure the sine wave signal. Better results with the obtained with the reference sine wave about 10 cycles than with fewer cycles. The wave signal is the first trans- transformed to a nearly linear waveform using the arcs cosine, and then the measured data which represent the ramp linearity is obtained by uh, tran- transforming all segments to have the same slope or fitting their segments together to form a single line. And the sine wave data to measure the performance of the different corrections, the effective things methods are used. The low harmonic distortion dBc and the 20 megahertz sine waveform signal and the consecuted and the reference signals, the different correction methods with the same 20 percentage of full scale input sine wave. The improvement using the internal CRO correction is about the factor of 2.5. The improvement of both static and time based external correction by the methods of this paper is a factor of 4, and the static dynamic corrections contributed almost equal to the improvement. And the exponential growth data, and the second measure of the performance uses an exponential signal. The waveform from two separate scope types are compared, and which is having the graph and the cross section of the correction which is more direction, indirect, direct guess and the waveforms. Thank you, sir. I hope you are understand, sir.